Good morning and welcome to the DVCon 2021 update on the Accelerator Multi-Language Working Group. Our presentation today consists of three sections. I am Warren Stapleton from AMD, and in the first section I will cover the problem statement, example use cases, high-level architectural requirements, the MLV architecture, a verification IP reuse case, the MLV API standard, and an overview of the software architecture. The next section will be presented by Martin Barnasconi from NXP, who will cover UVM SystemC and UVM SystemC requirements, learnings and findings, and a summary of where we're at. The third and final section will be a demo that will be presented by Faris Khundakjie from Intel. At the end of these presentations, we will save some time for broad Q&A. The mission of the MLV Working Group is to create a standard and functional reference for interoperability of multi-language verification environments and components. The Working Group has reviewed requirements and is developing an open-source proof-of-concept library for creating a standards-based approach for combining verification environments developed in different languages and frameworks. In addition, the group will look at ways to enable the introduction of the UVM concepts in other environments and languages that come from legacy projects or developed with frameworks other than SystemVerilog or SystemC for beneficial reasons. Verification engineers regularly encounter multi-language integration problems. The multi-language integration problem is not limited to SystemVerilog to SystemC, but can include models and stimulus in other languages such as VHDL, MATLAB, E, C, C++, and a plethora of interpreted languages such as Python, Ruby, Lua, for example. Many users share the same use cases, and most invest in redundant efforts with non-standard internal or vendor-specific solutions. The problem grows when mixing technologies from different vendors for their unique benefits. And here are some example use cases for the multi-language verification solution. The first use case to highlight is called verification IP reuse. This is where there is a desire to combine verification IP that has been written in different frameworks and/or languages into a coherent design verification environment. Another use case is where you have software-based stimulus. This is where a CPU or embedded controller with its own instruction set and associated program is used to stimulate the design. UVM-style sequences do not make sense in this case, but you may still need to have the software stimulus interact at a high level with other UVM-based stimulus. There are also use cases that are becoming much more common that involve reuse for the purpose of simulation acceleration. Reuse of SystemC reference and functional models in hardware-accelerated environments is common in this scenario, where a SystemVerilog test bench may not be present. And finally, legacy code reuse. Often verification environments or test cases from previous projects are one of the most valuable assets a team may have to get started with. The ability to do seamless integration of legacy test bench code and utilities written in different languages is a strong requirement for a successful multi-language solution. The working group had the following goals from the beginning: to standardize interoperability between multiple different verification frameworks through communication between the frameworks, coordination with phasing and synchronization primitives, and making common methodology facilities available across the entire system. The goal was also to simplify the integration of external verification IP and to deliver debug state and access methods for data that flows through the system. Furthermore, it should encompass emulation and hardware-assisted verification environments and to enable multiple implementations based on this standard. An early decision to support these goals was to adopt the following tenet: to follow UVM principles and support a superset of the UVM functionality, seeing that UVM is currently the leading verification methodology. Our working group's goals are to enrich the existing verification methodologies as opposed to writing a completely new approach. The working group collected a set of requirements from the following primary categories that are relevant for verification: system level, startup and shutdown, synchronization, phasing, communication, control and status, messaging, debug, register management, and testing for compliance of the final solution. In addition to identifying the key requirements and adopting some tenets, the working group agreed to the following guiding principles: to follow service-oriented framework concepts to facilitate the creation of scalable, modular, and layered architecture, to introduce adapters that bridge frameworks that have UVM capabilities to the overall system, like phasing, configuration, communication, those offered as services, and providing services that are selected using a resolution process. And to decouple the API from the implementation by standardizing the API with documentation and header files, providing a reference implementation, and facilitate the creation of more than one implementation so there is an opportunity for others to create these. This diagram shows an overview of the MLV architecture. It consists primarily of a collection of services that get registered in a service registry that are then selected and used by adapters that wrap the various pre-existing frameworks. The adapters have two roles, either to present an existing service to the service registry so that it can ultimately be used by other frameworks, or to either augment its own capabilities or replace an internal capability with one provided from elsewhere. There may be frameworks in the future that do not require an adapter. However, this is not currently the case. Even with UVM, there is a need to expose internals to the registry or provide the mechanism to take advantage of the externally provided services. The control interface is the final piece that provides overall control and configuration of the MLV solution. Here is an example of how this service-oriented architecture would be used to enable reuse of some verification IP. In this case, the UVM SystemC scoreboard is connected to the system through a UVM SystemC adapter, and the stimulus is provided from a UVM SystemVerilog environment that uses the UVM SystemVerilog adapter to drive the device under test, which is not actually shown in this diagram. This diagram shows an overview of the MLV software architecture. The main focus of the working group is to develop an API that supports the interaction between the adapters and the underlying implementation, while the team is also developing a reference implementation and also some example adapters as part of the overall proof of concept. Those parts are not being standardized. The team has initially been focusing on a subset of the overall functionality. The first items we worked on were the lifecycle events such as startup and shutdown, interacting with the verification component hierarchy, and phasing. Hierarchy is a complex issue in a multi-language system because it is possible to be entering and exiting different languages and frameworks multiple times as you traverse down the hierarchy. Phasing refers to a mechanism used to coordinate high-level activities and execution through a test. For example, there could be a reset phase, followed by initialization for the design, followed by some test-focused activity, and then a quiescing phase as the system shuts down before finally exiting the test. Each one of the services provided can potentially have two sides or roles. Firstly, there are interfaces that provide services to the outside world from the MLV implementation. These are called import interfaces. Secondly, there is the reverse, interfaces through which an adapter provides a capability to the implementation side. These are called export interfaces. The purpose of the MLV standard is to provide a precise definition of these import and export interfaces. The group has adopted a naming convention for all of the API calls. The implementation code itself has adopted a style guide that is well known that was published by Google. The API calls follow the pattern of MLV, then followed by a category which mostly matches the service area, then actor role, followed by an import or export direction, and then a type, which is typically IF standing for interface. An example from the phasing API is MLV phase participant export interface. Here is an example from the current proposed API for the TLM aspect of the standard. You can see how it is split along import and export roles. We've also differentiated between the TLM1, TLM2, and analysis interfaces. The next portion of this presentation will be about requirements presented by Martin.
Thanks, Warren, for introducing the multi-language standard. We also captured requirements for related standardization efforts such as UVM, UVM in SystemC, and SystemC itself. One of our recommendations is to review existing language standards and implementations and assess their capabilities for seamless integration in a multi-language framework. Note that we are not aiming at changing these existing capabilities. Instead, we're considering adding a few additional methods dedicated to multi-language support. The overarching principle is to apply the separations of concern design principle, where the design hierarchy is independent from the verification, thus test bench hierarchy. UVM in SystemVerilog is compliant with this approach, where the design intent is captured in modules and verification components in classes. However, UVM in SystemC does not apply to this approach, because both design and verification components are based on SystemC modules. Perhaps this limitation, which might be caused by constraints in the reference implementation, can be addressed in the future. Additional requirements for a multi-language environment is how to apply time synchronization between the different verification components residing in different frameworks, which are most likely controlled by different execution or simulation engines. It is important that for proper synchronization, there is agreement on the exact synchronization point in time. This means the specified time should be reached and simulation synchronization occurs at the first delta cycle and not before. Currently, we are observing an issue in SystemC which needs to be addressed. Another requirement relates to the decoupling of the test bench creation during elaboration and the start of simulation. Today in UVM, this is all executed in a single function called runTest. However, the preference is to have this separated in a dedicated call for elaboration, so different frameworks can execute their elaboration phase. After this, one framework will start the simulation by calling a dedicated start function. Some final words on the learnings and findings we observed as part of this multi-language standardization activity. We've seen that we are dealing with a complex problem. We had to make a decision. Do we prefer to build upon capabilities but also limitations of existing verification frameworks? Or do we build something from scratch? Obviously, the preference was to leverage existing development technologies and adapt them to a multi-language scenario. For example, we've used the UVM multi-language technology which was available in the industry. We also experienced some practical challenges. For example, who owns a specific service like phasing or communication when such service is also used outside its own framework? Furthermore, we would like to introduce new capabilities, but at the same time not breaking existing user code. Another practical limitation were the limited resources in the working group to define the API and the implementation. Important to mention is that the multi-language challenge is recognized in the industry and that there is a strong commitment from companies like Intel, AMD, NXP and Cadence to support this standardization initiative. However, we can use more help, so feel free to contact us if you'd like to contribute. This summary concludes our presentation on the multi-language verification standardization. The first API proposals are defined by the multi-language verification working group and are now being implemented and validated. To make the community aware of this standardization initiative, We have presented a similar story at the SystemC Evolution Day in October last year, with the aim to address some of the SystemC standardization aspects. Development of the demonstrator is ongoing, and we have a partially implemented reference available, which we will also present in a second. The next steps for the standardization and working group is to continue development of the TLM communication. Furthermore, we like to extend the demo to show additional languages and frameworks, such as SystemVerilog. And most importantly, we will document the API in a language reference manual. We are always open to explore new engagements and collaborations, which help to develop this multi-language verification standard. Any additional help and contributions are appreciated, so feel free to contact us if you like to join the standardization working group using the email address shown here. We are reaching the end of our presentation, but please stay connected since we will continue with a live demonstration of the multi-language verification capabilities. Faris will demonstrate the lifecycle concepts, including startup and shutdown, as well as the phasing of verification components. After this demo, we are happy to answer any questions you might have in the Q&A session.